Right. Hi, guys. Hopefully this is recording. Um, I would like you today to start looking at patterns in quadratic graphs. So to start, you are given 6 different sets of data, and some of the data is linear, some of the data is quadratic, and some is something else. So I just kind of picked different random functions. I'll give you the hint that there's 2 of each. Okay, so from this list, there's 2 linear, there's 2 quadratic, and there's 2 something else. One other hint is look at the differences between the y values. Okay, in each sequence, the x coordinates are always consistent. They don't necessarily have to go up, by consecutive integers like this last one, but as long as your x coordinates are consistent, what you can do is look at the comparison between the y values. And you know what that would look like if the data is linear. I want you to think about what that would look like if it's quadratic. So, one quadratic pattern that we did was the n squared from the apple orchard problem. So think about what those different y values look like, and then use that relationship you saw to figure out which ones are quadratic. Okay, I'll have an answer key in the class when you're done. The other thing that I want you to do today is to think about how a stretch factor affects the graph. And so if you need to pause the movie now to do the front, that's fine, but this is the back side. So on Tuesday, we introduced you to what factored form for a quadratic looks like. And we saw that, that's a 2. R1 and R2 represented the roots or the x-intercepts for the graph. And then we looked on Desmos and saw that A does this like stretching and reflecting thing with the graph. So I want to show you how you can kind of relate A to what's happening with the graph. So let's start with just the generic x squared graph. This is what's called the parent function, and that's because all other quadratics will have the same shape as x squared, and they'll behave the same way as just y equals x squared. So let's just test with some different values for x. 3. Okay, so if x is -2, it's the quantity -2 squared, and we get 4. And then -1 quantity squared is 1. 0 squared is 0. 1 squared is 1. Oh, why did I write 1 twice? 2 squared is 4. 3 squared is 9. So let's plot those points. 0, 0, and then 1, 1, -1, 1, 2, 4, and -2, 4, 3, 9, and -3, 9. And so those are the points that we can fit on the coordinate grid that we're provided. When you graph a line, you have to graph at least 2 points. When you graph a quadratic, you have to graph at least 3 points, and that's because it's nonlinear. So, ideally one of those points is your vertex, right? And then, if it's something else, we could be graphing the x-intercept or the y-intercept. In this case, we can use by symmetry, we can find some different points on either side. So I want you to think about the pattern of these numbers, okay? One pattern is just that whatever the x value is, it's that thing squared gets you the y value. So I'm going to show that on the left-hand side. If you go over 1, you go up 1 unit. If you go over 2 from the vertex, well, 2 squared is 4. So you go up 4 units. If you go over 3, 3 squared is 9, you'd go up 9 units. So using the idea that the difference from the vertex is related to the x, it's just the square of whatever that x coordinate is, or from the vertex. So from the vertex, the vertical change is that we can go up 1, up 4, up 9, up 16, and so forth, up 25, up 36. Okay, they're all perfect squares. Another way to think about a pattern that's evolving from our graph or from the table is the difference. So what's the difference as we kind of work our way through this table? From 0 to 1, we go up 1, and then from 1 to 4, we go up 3. From 4 to 9, we go up 5. So then it follows the next one, we go up 7, which is right, because the next one will be 16. So you can also think about that pattern of points is from the vertex. You just go up 1, so it's over 1, up 1. And then the next time you go over, it's from that point you just plotted. So just over 1, and then up 3. And then from that point, over 1, up 5. And then over 1, up 7, and so forth. Okay, so explaining that pattern, we have from the previous point plotted, we're still talking about the vertical change. Then it goes up 1, up 3, up 5, up 7, and so forth. So this is just the generic y equals x squared graph. We're going to see how that compares to y equals 2x squared. Okay. So the vertex in this case is still at 0, 0 because when you have x be 0, 0 squared is 0 times 2 is 0. So let's make a table of values. We know it goes through 0, 0. So with 1 squared is 1 times 2 is 2. With x is 2. 2 squared is 4 times 2 is 8. 3 squared is 9 times 2 is 18. And then the opposite is just the reflectional points. So from 0, 0, with this one, 1, 2, and negative 1, 2. And then 2, 8, and negative 2, 8. 3, 18 ended up being off our graph. All right, so visually, what happened? Okay, our graph originally was a little wider. Now it appears narrower, and that's because the y values all got bigger. Okay, the x values stayed the same, but what happened to the y values when you compare the columns of y values? Well, these y values are just twice as big. And that makes sense because in the equation, we're taking the original x squared and we're just multiplying that output times 2. So all of the outputs or all of the y values are being doubled. Okay. How that relates to our pattern. Okay, from your vertex, it's really just where you're going to take 2 times the change. So where originally we went up 1, now we're going to go up 2 times 1. Originally we went up 4, now we'll go up 8, 2 times 4. Originally we went up 9, so now we'll go up 18, and then 32, and so forth. So on the graph, we can see that, and this is just from the vertex again. So we went over 1, up 2, and then if we go over 2, we went up 8, and then over 3, up 18, and so forth. Okay, so we're just taking the original vertical shift or vertical distance from the vertex, and we just doubled each one of those amounts. If you use the idea from the previous point, it's the same idea, it's just 2 times that change. Okay, so where originally we went up 1, now we're going to go up 2. We went up 3 before, so now we'll go up 6. We went up 5, so now we'll go up 10, up 14, and so forth. Okay, so 6, 10, 2, 6, 10, 14. From our vertex, the first time we go over, we go up 2. And then from that point, we can go up 6, go over 1 up 6, and then we can go over 1 up 10, and so forth. So it follows that you should know, sorry, the lights are off. There we go. Okay, I'm back. You should know what it would look like to do a 3x squared or a 5x squared. Okay, each one of those changes, you just take the original pattern and you multiply by what that stretch factor is. So if you're multiplying by a number bigger than 1, it's going to make your graph appear skinnier because you're making larger vertical jumps. Okay, so the last example, well, what happens if a is negative and what happens if a is less than 1? Let's make our table. Okay, so if x is 0, same thing as before, right? 0 squared is 0 times negative 1/3 is 0. So this one as well, we'll go through the origin. The next one, 1. 1 squared is 1 times negative 1/3 is negative 1/3. How about 2? 2 squared is 4. 4 times negative 1/3 is negative 4/3. And then 3 squared is 9. And then 9 times negative 1/3 is negative 3. I'll say that one again. 9 times negative 1/3 is negative 3. And then by symmetry, we know the other points were negative 1/3 and negative 4/3. Okay, these will be kind of harder to plot. Over 1, down 1/3. I'm just going to jump out to the integer. Over 3, down 3. I wonder if there's another integer point that we can plot. Okay, for it to be an integer, whatever the squared number is, has to be divisible by 3 for it to produce like a nice pretty integer. So, so the next number would be, what, 416? That's not divisible by 3. 5 is 25. No. 6, 36. Yeah, okay, so the next point would be 6. 6 squared is 36 times negative 1/3 is negative 12. So we know if we go over 6, we would go down to negative 12, which is off our graph. And you could go that way as well. So that tells us we at least have 3 integer coordinates on our graph. So what happens if a is negative is it does a reflection on our graph. And then what happens if a is less than 1, or specifically between 0 and 1, is it makes your graph appear wider. And that's because when it's larger than 1, you're making bigger vertical jumps. When your a is between 0 and 1, you end up making smaller vertical jumps. So the graph is going to appear wider. Okay. So looking at the patterns with this one, if we're working from the vertex, we just take negative 1/3 times whatever that change was. So the change originally was 1, 4, 9, 16, okay, and that was from the x-coordinates squared. So 1 times negative 1/3 is negative 1/3. We've got negative 4/3. Negative 9/3 is negative 3. Negative 16/3. Negative 25/3. Negative 12, and so forth. So that pattern continues. How we see that on the graph. From the origin, if we go left 1, we're only going to go down 1/3. Okay, that vertical distance we went down was only 1/3. If from the vertex, if we go over 2, we're going to go down 4/3. It's really hard to read. Negative 4/3. From the vertex, if we go 3, then we're going to go down 3. Okay, so if you base it just on the vertex, how much you go over, and then you multiply that vertical distance by negative 1/3. If you base it from the previous point, you take negative 1/3 times that vertical jump. So back with the original x squared, it was 1357. So we would take 1 times negative 1/3, 3 times negative 1/3, 5 times negative 1/3, 7 times negative 1/3, and so forth. So what this looks like is from the origin, we go right 1, we go down 1/3. And then from that point, we go right 1, we go down a whole 1 unit. Okay, does that mean we end on an integer? No, because the first time we moved, we only went down 1/3. Okay, so now we'd be at what, 2 1/3? Or no, 1 1/3. I lied, 1 1/3. Okay, and then if we go out one more time, over 1, down 5/3, that would get us down to that -3. So depending on what the stretch factor is, one might be easier to do than another. But the idea is when a is larger than 1, it makes your graph appear narrower because you have bigger jumps. And then when a is between 0 and 1, it makes your graph appear wider because you have shallower jumps. Okay, thanks guys, bye.